A complex number is a number that can be expressed in the form a plus by, where a and b are real numbers and I is the imaginary unit that satisfies the equation I2 equals -1. In this expression, a is the real part and b is the imaginary part of the complex number. Complex numbers extend the concept of the one-dimensional number line to the two-dimensional complex plane by using the horizontal axis for the real part and the vertical axis for the imaginary part. The complex number a plus by can be identified with the point in the complex plane. A complex number whose real part is 0 is said to be purely imaginary, whereas a complex number whose imaginary part is 0 is a real number. In this way, the complex numbers contain the ordinary real numbers while extending them in order to solve problems that cannot be solved with real numbers alone. As well as their use within mathematics, complex numbers have practical applications in many fields, including physics, chemistry, biology, economics, electrical engineering, and statistics. The Italian mathematician Gerolamo Cardano is the first known to have introduced complex numbers. He called them fictitious during his attempts to find solutions to cubic equations in the 16th century. Overview. Complex numbers allow for solutions to certain equations that have no solutions in real numbers. For example, the equation has no real solution, since the square of a real number cannot be negative. Complex numbers provide a solution to this problem. The idea is to extend the real numbers with the imaginary unit I where I2 equals -1, so that solutions to equations like the preceding one can be found. In this case the solutions are -1 plus 3i and -1 minus 3i, as can be verified using the fact that I2 equals -1. According to the fundamental theorem of algebra, all polynomial equations with real or complex coefficients in a single variable have a solution in complex numbers. Definition: a complex number is a number of the form a plus by, where a and b are real numbers and I is the imaginary unit, satisfying I2 equals -1. For example, -3.5 plus 2i is a complex number. The real number a is called the real part of the complex number a plus by. The real number b is called the imaginary part of a plus by. By this convention, the imaginary part does not include the imaginary unit. Hence b, not by, is the imaginary part. The real part of a complex number z is denoted by re, or the imaginary part of a complex number z is denoted by im or. For example, hence, in terms of its real and imaginary parts, a complex number z is equal to. This expression is sometimes known as the Cartesian form of z. A real number a can be regarded as a complex number a plus 0i whose imaginary part is 0. A purely imaginary number bi is a complex number 0 plus bi whose real part is 0. It is common to write a for a plus 0i and bi for 0 plus bi. Moreover, when the imaginary part is negative, it is common to write a minus bi with b greater than 0 instead of a plus I. For example, 3 minus 4i instead of 3 plus I. The set of all complex numbers is denoted by or notation. Some authors write a plus ib instead of a plus bi, particularly when b is a radical. In some disciplines, in particular electromagnetism and electrical engineering, j is used instead of I, since I is frequently used for electric current. In these cases, complex numbers are written as a plus bj or a plus jb. Complex plane. A complex number can be viewed as a point or position vector in a two-dimensional Cartesian coordinate system called the complex plane, or Argand diagram, named after John Robert Argand. The numbers are conventionally plotted using the real part as the horizontal component, and imaginary part as vertical. These two values used to identify a given complex number are therefore called its Cartesian, rectangular, or algebraic form. A position vector may also be defined in terms of its magnitude and direction relative to the origin. These are emphasized in a complex number's polar form. Using the polar form of the complex number in calculations may lead to a more intuitive interpretation of mathematical results. Notably, the operations of addition and multiplication take on a very natural geometric character when complex numbers are viewed as position vectors. Addition corresponds to vector addition, while multiplication corresponds to multiplying their magnitudes and adding their arguments. Viewed in this way, the multiplication of a complex number by I corresponds to rotating the position vector counterclockwise by a quarter turnabout. The origin, I equals I plus by 2 equals B plus I. History in brief. Main section. History. The solution in radicals of a general cubic equation contains the square roots of negative numbers when all three roots are real numbers. A situation that cannot be rectified by factoring aided by the rational root test if the cubic is irreducible. This conundrum led Italian mathematician Girolamo Cardano to conceive of complex numbers in around 1545, though his understanding was rudimentary. Work on the problem of general polynomials ultimately led to the fundamental theorem of algebra, which shows that with complex numbers, a solution exists to every polynomial equation of degree 1 or higher. Complex numbers thus form an algebraically closed field, where any polynomial equation has a root. Many mathematicians contributed to the full development of complex numbers. The rules for addition, subtraction, multiplication, and division of complex numbers were developed by the Italian mathematician Raphael Bombelli. A more abstract formalism for the complex numbers was further developed by the Irish mathematician William Rowan Hamilton, who extended this abstraction to the theory of quaternions. Relations. Equality. Two complex numbers are equal if and only if both their real and imaginary parts are equal. In symbols. Ordering. Because complex numbers are naturally thought of as existing on a two-dimensional plane, there is no natural linear ordering on the set of complex numbers. There is no linear ordering on the complex numbers that is compatible with addition and multiplication. Formally, we say that the complex numbers cannot have the structure of an ordered field. This is because any square in an ordered field is at least 0, but I2 equals -1. Elementary operations. Conjugate. The complex conjugate of the complex number z equals x plus y is defined to be x minus y. It is denoted or z asterisk. Formally, for any complex number z, geometrically, is the reflection of z about the real axis. Conjugating twice gives the original complex number. The real and imaginary parts of a complex number z can be extracted using the conjugate. Moreover, a complex number is real if and only if it equals its conjugate. Conjugation distributes over the standard arithmetic operations. Addition and subtraction. Complex numbers are added by adding the real and imaginary parts of the summands. That is to say, similarly, subtraction is defined by using the visualization of complex numbers in the complex plane. The addition has the following geometric interpretation. The sum of two complex numbers a and b, interpreted as points of the complex plane, is the point x obtained by building a parallelogram 3 of whose vertices are O, A and B. Equivalently, x is the point such that the triangles with vertices O, A, B, and X, B, A are congruent. Multiplication and division. The multiplication of two complex numbers is defined by the following formula. In particular, the square of the imaginary unit is -1. The preceding definition of multiplication of general complex numbers follows naturally from this fundamental property of the imaginary unit. Indeed, if I is treated as a number so that d means d times I, the above multiplication rule is identical to the usual rule for multiplying two sums of two terms. The division of two complex numbers is defined in terms of complex multiplication, which is described above, and real division. When at least one of C and D is non-zero, we have division can be defined in this way because of the following observation. As shown earlier, C minus di is the complex conjugate of the denominator C plus di. At least one of the real parts C and the imaginary part D of the denominator must be non-zero for division to be defined. This is called rationalization of the denominator. Reciprocal. The reciprocal of a non-zero complex number z equals x plus y is given by this formula, can be used to compute the multiplicative inverse of a complex number if it is given in rectangular coordinates. In the network analysis of electrical circuits, the complex conjugate is used in finding the equivalent impedance when the maximum power transfer theorem is used. The square roots of a plus by r, where and where SGN is the signum function. This can be seen by squaring to obtain the plus by. Here is called the modulus of a plus by, and the square root sign indicates the square root with non-negative real part, called the principal square root. Also, where polar form, absolute value, an argument. An alternative way of defining a point P in the complex plane, other than using the x and y coordinates, is to use the distance of the point from O, the point whose coordinates are, together with the angle subtended between the positive real axis and the line segment up in a counterclockwise direction. This idea leads to the polar form of complex numbers. The absolute value of a complex number z equals x plus y is if z is a real number, then r equals x. In general, by Pythagoras' theorem, r is the distance of the point P representing the complex number z to the origin. The square of the absolute value is where is the complex conjugative. The argument of z is the angle of the radius up with the positive real axis, and is written as with the modulus. The argument can be found from the rectangular form. The value of phi is expressed in radians in this article. It can increase by any integer, multiple of 2 pi, and still give the same angle. Hence, the arg function is sometimes considered as multi-valued. Normally, as given above, the principal value in the interval are obtained by adding 2 pi if the value is negative. The polar angle for the complex number 0 is indeterminate, but arbitrary choice of the angle 0 is common. The value of phi equals the result of at in 2. Together, r and phi give another way of representing complex numbers, the polar form. As the combination of modulus and argument fully specify the position of the point on the plane, recovering the original rectangular coordinates from the polar form is done by the formula called trigonometric form using Eulers' formula. This can be written as using the size function. This is sometimes abbreviated to in angle notation, often used in electronics to represent a phasor with amplitude r and phase phi. It is written as multiplication and division in polar form. Formulas for multiplication, division and exponentiation are simpler in polar form than the corresponding formulas in Cartesian coordinates. Given two complex numbers z1 equals r1 and z2 equals r2, because of the well-known trigonometric identities we may derive, in other words, the absolute values are multiplied and the arguments are added to yield the polar form of the product. For example, multiplying by I corresponds to a quarter turn counterclockwise, which gives back I2 equals -1. The picture at the right illustrates the multiplication of, since the real and imaginary part of 5 plus 5 are equal. The argument of that number is 45 degrees, or pi 4. On the other hand, it is also the sum of the angles at the origin of the red and blue triangles, or arctan and arctan, respectively. Thus, the formula holds. As the arctan function can be approximated highly efficiently, formulas like this, known as match and like formulas, are used for high-precision approximations of pi. Similarly, division is given by exponentiation. Euler's formula states that, for any real number x, where e is the base of the natural logarithm, this can be proved through induction by observing that and so on, and by considering the Taylor series expansions of EIX, cos and sin. The rearrangement of terms is justified because each series is absolutely convergent. Natural logarithm Euler's formula allows us to observe that, for any complex number where r is a non-negative real number, one possible value for z's natural logarithm is because cos and sin are periodic functions. The natural logarithm may be considered a multi-valued function. With integer and fractional exponents we may use the identity to define complex exponentiation, which is likewise multi-valued. When n is an integer, this simplifies to de Moivre's formula. The nth roots of z are given by for any integer k satisfying 0 kn-1. Here n square root r is the usual nth root of the positive real number r, while the nth root of a positive real number r is chosen to be the positive real number c satisfying Cn equals x. There is no natural way of distinguishing one particular complex nth root of a complex number. Therefore, the nth root of z is considered as a multi-valued function, as opposed to a usual function f, for which f is a uniquely defined number. Formulas such as do in general not hold for complex numbers. Properties. Field structure. The set C of complex numbers is a field. Briefly, this means that the following facts hold. First, any two complex numbers can be added and multiplied to yield another complex number. Second, for any complex number z, its additive inverse minus z is also a complex number. And third, every non-zero complex number has a reciprocal complex number. Moreover, these operations satisfy a number of laws. For example, the law of commutativity of addition and multiplication for any two complex numbers z1 and z2. These two laws and the other requirements on a field can be proven by the formulas given above, using the fact that the real numbers themselves form a field. Unlike the rails, C is not an ordered field, that is to say, it is not possible to define a relation z1 less than z2 that is compatible with the addition and multiplication. In fact, in any ordered field, the square of any element is necessarily positive, so I2 equals -1 precludes the existence of an ordering on C, when the underlying field for a mathematical topic or construct is the field of complex numbers. The topic's name is usually modified to reflect that fact. For example, complex analysis, complex matrix, complex polynomial, and complex Lie algebra. Solutions of polynomial equations given any complex numbers a0, and the equation has at least one complex solution z, provided that at least one of the higher coefficients a1, and is non-zero. This is the statement of the fundamental theorem of algebra. Because of this fact, C is called an algebraically closed field. This property does not hold for the field of rational numbers Q nor the real numbers R. There are various proofs of this theorem, either by analytic methods such as Liouville's theorem, or topological ones such as the winding number, or a proof combining Galois theory and the fact that any real polynomial of odd degree has at least one real root. Because of this fact, theorems that hold for any algebraically closed field apply to C. For example, any non-empty complex square matrix has at least one eigenvalue. Algebraic characterization. The field C has the following three properties. First, it has characteristic 0. This means that 1 plus 1 plus 1 0 for any number of summands. Second, its transcendence degree over Q, the prime field of C, is the cardinality of the continuum. Third, it is algebraically closed. It can be shown that any field having these properties is isomorphic to C. For example, the algebraic closure of QP also satisfies these three properties, so these two fields are isomorphic. Also, C is isomorphic to the field of complex Puiseux series. However, specifying an isomorphism requires the axiom of choice. Another consequence of this algebraic characterization is that C contains many proper subfields that are isomorphic to C. Characterization as a topological field. The preceding characterization of C describes only the algebraic aspects of C, that is to say, the properties of nearness and contiguity, which matter in areas such as analysis and topology, are not dealt with. The following description of C as a topological field does take into account the topological properties. C contains a subset P of non-zero elements satisfying the following three conditions. P is closed under addition, multiplication and taking inverses. If x and y are distinct elements of P, then either x minus y or y minus x is in P. If S is any non-empty subset of P, then S plus P equals x plus P for some x in C. Moreover, C has a non-trivial involutive automorphism XX*, such that XX* is in P for any non-zero x in C. Any field F with these properties can be endowed with a topology by taking the sets B equals y, P minus * P, as a base, where X ranges over the field and P ranges over P. With this topology, F is isomorphic as a topological field to C. The only connected locally compact topological fields are R and C. This gives another characterization of C as a topological field, since C can be distinguished from R because the non-zero complex numbers are connected, while the non-zero real numbers are not.